Welcome to machines built for a future that didn't exist yet. Too smart, too complex, too early. Farmers weren't ready. Fields weren't ready. The industry wasn't ready. These didn't fail from weakness. They failed from being ahead of time. Number 1. Case turbine tractor. In the mid-1950s, Case did something no other farm equipment company dared to try. They built a tractor powered by a gas turbine engine, the same type of engine used in aircraft. This wasn't a fantasy project. Case built working machines. They plowed fields. They pulled implements. They ran for thousands of hours. One of them even logged over 8,000 operating hours on a Nebraska farm. The turbine tractor had almost no vibration. It had only a handful of moving parts. It could run on diesel, kerosene, jet fuel, even low-grade oil. It started instantly in cold weather. It never stalled under load. It produced smooth, continuous power that piston engines could not match. On paper, it was the perfect farm engine. In reality, it terrified people. The exhaust temperature could melt asphalt. The engine screamed at 35,000 RPM. Fuel consumption at idle was brutal. Throttle response felt alien to operators raised on pistons and clutches. Farmers were used to engines they could hear, feel, and understand. The turbine had no lug, no familiar rhythm. When something went wrong, there was nothing to adjust. No carburetor, no valves, no injectors. It was either working or it wasn't. Maintenance was another barrier. Turbines required aerospace-level tolerances. Dust and debris shortened component life. Dealers had no tools or training for jet engines. And then there was cost. A turbine tractor cost more than multiple conventional machines combined. At a time when diesel engines were becoming cheaper, stronger, and easier to service, Case was offering farmers a machine that belonged in an airport hangar. The tractor wasn't flawed. The world around it was. Decades later, turbines found their place in tanks, ships, power stations, and aircraft, exactly where high-speed, low-vibration engines make sense. But agriculture wasn't ready for aerospace technology. Case shut the project down. The turbine tractor didn't fail because it was impractical. It failed because it asked 1950s farms to operate in the future. It wasn't a tractor. It was a jet engine searching for a century that hadn't arrived yet. Number 2. Ford Selecto-Speed Tractors, 1959 to 1964. In 1959, Ford launched one of the most ambitious transmission systems ever put into a farm tractor, Selecto-Speed. It was a fully Powershift gearbox offering 10 forward speeds without clutching. Farmers could shift on the move, under load, at any throttle position, something unheard of in agricultural equipment at the time. The system was revolutionary. Modern tractors now use continuously variable or full Powershift transmissions as standard. But in 1959, this level of automation collided with reality. The Selecto-Speed transmission relied on hydraulic pressure, precision bands, planetary gear sets, and complex valve bodies. It required exact adjustment and clean oil. Rural mechanics were trained in clutches and gears, not hydraulic logic systems. Early units suffered from band failures, pressure loss, and misadjustment. Even small errors caused slipping, overheating, or total failure. Worse, the system felt alien. Farmers were used to mechanical feedback, clutch feel, gear engagement, engine lug. Selecto-Speed removed those sensations. When something went wrong, operators didn't know why. They blamed the machine. Ford attempted updates, issuing multiple revisions, but the damage to reputation was permanent. Dealers struggled to service the units. Owners lost confidence. Used values collapsed. Many tractors were retrofitted back to manual transmissions. The tragedy is that the core idea was sound. Powershift transmissions are now the backbone of modern agriculture. But in 1959, oil filtration standards were primitive. Dealer training was insufficient. Diagnostic tools didn't exist. Farmers distrusted invisible automation. Selecto-Speed was not wrong. It was early. Ford tried to leap decades ahead in one step, and the market refused to follow. It remains one of the clearest examples of a machine failing not from incompetence but from arriving before its users were ready. Number 3. John Deere 80110, 1960. In 1960, John Deere introduced the 8010, a four-wheel drive articulated tractor producing over 200 horsepower. It dwarfed anything on American farms at the time. This was not a prototype. it was sold commercially. Roughly 100 units were built. The 8010 was designed for large-scale farming that barely existed yet. Its size demanded wide fields, massive implements, and logistics infrastructure that most operations did not have. Roads, bridges, trailers, and service shops were not built for machines of this scale. Mechanically, it was incredibly complex. It used dual engines, massive gearboxes, hydraulic articulation, and custom components that shared little with existing Deere products. Dealers lacked parts. Mechanics lacked experience. Transporting it between fields required planning and equipment most farmers didn't own. Economically, it was impossible to justify. Most farms could not use its capacity efficiently. The tractor's potential outpaced the tools of its time. There were few implements wide or strong enough to exploit its power. It became an expensive symbol of excess. John Deere learned from the failure. A decade later, when large-scale farming, air seeders, and massive tillage tools became common, Deere returned with refined articulated designs, the 7020 series, that succeeded spectacularly. The 8110 failed, not because it was impractical, but because the world around it had not grown large enough to need it. Number 4. Allis-Chalmers Roto-Baler. 1949, the Allis-Chalmers Roto-Baler was the world's first commercially successful round baler. It produced compact, twine-wrapped cylindrical bales automatically. Today, round balers dominate global hay production. In 1950, however, this machine failed commercially. Farmers were accustomed to square bales. Barns, wagons, elevators, and labor systems were built around them. The Roto-Baler introduced a new bale shape that required new handling methods. Early round bales were small but awkward. They rolled. They didn't stack. They didn't fit barns. Mechanically, the machine was intricate. Chains, belts, rollers, wrapping systems, all working in dusty, fibrous conditions. Maintenance was higher than square balers. When breakdowns occurred, farmers lacked experience diagnosing them. The Roto-Baler was correct about the future, but it asked farmers to change. Storage buildings, transport methods, labor routine, equipment ecosystem. Most refused. Sales stagnated. Production ended. 2 decades later, large round balers returned. Simpler, stronger, supported by redesigned farms. What failed in 1950 became standard by 1980. The Roto-Baler did not lose because it was bad. It lost because it tried to change everything at once. Number 5. Minneapolis-Moline Uni-System, 1961 to 1970. In 1961, Minneapolis-Moline launched one of the boldest agricultural machines ever sold, the Uni-System. Unlike conventional tractors, the Uni was designed as a modular power unit. The front half contained the engine, cab, drivetrain, and operator controls. The rear half could be swapped entirely: corn picker, combine harvester, forage harvester, swather, or planter, by rolling one module away and attaching another. On paper, it was brilliant. One power unit could replace several machines. Farmers could buy one tractor and expand its role across seasons. In practice, it failed because it asked farmers to abandon the entire logic of how farms were organized. The Uni-System required a radically different workflow. Implements were no longer towed, they became structural components of the machine. Storage buildings had to be redesigned. Seasonal changeovers required space, hoists, and precision alignment. A farmer could not simply hitch and go. The machine demanded planning and mechanical confidence beyond what most operations had. Economically, the system was risky. A breakdown in the power unit halted every operation. With conventional equipment, a farmer could park one tractor and continue working with another. With the Uni, everything depended on one core machine. That level of dependency felt dangerous in an industry where timing is everything. Maintenance compounded the problem. Each module had specialized parts. Dealers had to stock inventories for a machine that few customers owned. Technicians needed training across multiple disciplines. When support lagged, confidence collapsed. Ironically, the Uni-System was conceptually decades ahead. Modern self-propelled harvesters, modular tool carriers, and even autonomous platforms now pursue the same one power unit, many roles idea. But in the 1960s, farms were not structured for it, and neither were dealers. Minneapolis-Moline eventually exited the project. The Uni became a legend, a machine that imagined the future correctly, but demanded that the present change too fast. Number 6. John Deere. Number 55 Hillside Combine, 1958 to 1964. The John Deere number 55 Hillside Combine was built for extreme terrain. Unlike conventional combines, it used hydraulic leveling systems to keep the threshing and cleaning systems horizontal on steep slopes. In mountainous farming regions, this was a technical marvel. The machine worked. It could operate on grades that would spill grain from ordinary combines, but it failed commercially because its complexity far exceeded the size of the market it served. Hydraulic leveling introduced sensors, pumps, cylinders, and control valves exposed to dust and vibration. A failure did not simply reduce comfort, it disabled harvesting. Maintenance required hydraulic expertise, uncommon in small rural shops. Operators had to understand a system that behaved differently from any other machine on the farm. The Hillside Combine also cost significantly more than standard models. Yet only a narrow band of farmers truly needed it. Most could operate standard machines with careful technique. For many, the cost of complexity outweighed the benefit. John Deere learned from this. Later Hillside machines were simpler, more robust, and built for specialized regions with dedicated dealer support. The Novar 55 was not wrong. It was simply too advanced for a market that was too small and unprepared. Number 7. Massey Ferguson. Ferguson System Implements, late 1940s, 1950s. Harry Ferguson's three-point hitch revolutionized agriculture. But Ferguson pushed the idea further. He envisioned tractors and implements as a single engineered system. Massey Ferguson sold implements that depended on hydraulic draft control, weight transfer, and precise geometry. The problem was not technical. It was cultural. Farmers were accustomed to mixing brands. They owned plows from one maker, seeders from another, tractors from a third. The Ferguson system worked best when everything matched. That meant abandoning existing equipment. Early Ferguson implements were lighter and more advanced, but farmers distrusted them. They appeared fragile compared to heavy, overbuilt traditional tools. Draft control was invisible. Farmers could not see what the hydraulics were doing. When something felt wrong, they blamed the system. The concept ultimately succeeded, industry-wide. Today, three-point hitches and draft control are universal, but Ferguson's original integrated ecosystem struggled because it arrived before farmers accepted that tractors and implements could be one intelligent system rather than independent tools. Number 8. Steiger Bearcat. Series 1. 1963 to 1967. The original Steiger Bearcat was among the first articulated four-wheel drive tractors sold in North America. It delivered unprecedented traction and horsepower. It was designed for vast fields and massive implements that barely existed. Early Bearcats were hand-built, powerful, and mechanically exotic compared to row crop tractors. Transporting them required trailers and permits farmers didn't own. Service networks were thin. Parts often had to be fabricated or shipped from distant suppliers. The machine was correct about the future. Large-scale farming, wide implements, and high-horsepower tractors would become standard. But in the 1960s, few farms could justify such capacity. The Bearcat outpaced the ecosystem. Roads, shops, tools, and even operator expectations. Steiger survived only because it refined the idea and waited for farms to grow into it. The early Bearcats failed commercially, but they defined what modern articulated tractors would become. Number 9. Hesston Stack Mover System, 1970s. Hesston pioneered large rectangular hay bales and developed the stack mover, a self-propelled machine that could lift, stack, and transport enormous bales. It transformed hay handling on paper. In reality, farms lacked the storage structures, roadways, and transport vehicles to exploit it. Barn doors were too small. Wagons were too weak. Buyers for massive bales were rare. The stack mover solved a problem that most farms did not yet have. Maintenance was heavy. The machine was specialized and seasonal. For many operators, it sat idle for months. When it broke, parts were expensive and technicians scarce. Large square bales eventually became dominant, but only after markets, barns, trucks, and export logistics evolved. The stack mover arrived before the hay economy could support it. Number 10. Claas Dominator. Electronic, 1980s. In the early 1980s, Claas introduced electronically monitored combines with onboard diagnostics, yield sensors, and performance displays. Operators could see losses, throughput, and efficiency in real time. It was revolutionary and unsettling. Farmers trusted sound, vibration, and experience. Now a screen told them what was happening inside sealed machinery. When numbers conflicted with instinct, the screen lost. Early electronics were fragile. Dust, moisture, and vibration caused failures. Replacement parts were expensive and slow. Many operators disabled systems they didn't trust. Dealers struggled to explain diagnostics to customers unfamiliar with digital logic. The machines were mechanically excellent, but the electronic layer alienated users. Today, digital harvest monitoring is universal. But in the 1980s, Claas proved that technology can be right and still fail if the human element isn't ready. These machines proved a hard truth. Being first can be fatal. They didn't break. The world just couldn't keep up. Innovation doesn't always win. Sometimes it arrives too soon.